So Ajit, you can start.
It's showing can't share content. You can't share the content unless the host or co-host. So please make me co-host. Now it's showing you a presenter.
Okay.
So I hope now it's visible to all, right?
Yeah, right.
Yeah, okay. So thank you, Raghav. So for introducing me. Before I begin, let me express my best wishes and congratulations to Professor Mudli for successful completion of 10 successful years. So in Spintronics at IIT Delhi. So to begin my presentation, I will present on tuning of magnetic properties in ferrimagnetic system using ion irradiation technique. So this is my outline of my presentation. I'll first introduce the a ferromagnetic system and the rational study. I mean, why we are studying this system and the ion irradiation technique. And using this ion irradiation technique, we tune the magnetic properties. First, I will introduce few systems, reported system, and then I'll go to my system. Then conclusion. Then acknowledgements. So, if you see a book definition, the definition of ferrimagnetic system, if the two sublattices are anti-parallel to each other, and one of the sublattice magnetic moment is lesser than other, so you see a ferrimagnetic nature here. However, if you add a rare earth and transcendental system and to form a ferrimagnetic system, so if you see the microscopic view, so the system forms something like this. So this is known as a ferrimagnetic distribution. However, the resultant of the magnetic moment, we see the anti-parallel to each other. So the resultant magnetization towards the rear earth magnetic moment. So let's see the importance of this ferrimagnetic system. Yes, this system can provide the large strength of PMA values as compared to COPT multilayer and other cases. And also this system can host the magnetic skirmion. So this is supposed to be the next generation storage device. And in this system, as this is anti-parallel to each other coupling, so you can reduce the stray field contribution so that you can minimize the Skyrmian Hall effect, so you can get the output at the desired location. And of course, if you see, as like previous speaker spoke about the oxide, if you make the oxide of this one ferrimagnetic insulator like YIG, there you can get the ultra low magnetic damping, so that that will be useful for ultra low power consumption. So in that case, so here we are interested to tune the magnetic properties by external potter like RTP or other thing. But here, the problem with the thermal treatment, like rapid thermal processing, there will be difficult to control the high roughness. I mean, due to the roughness, we cannot control that. So here you use the external potter like ion irradiation. So there you can minimize the surface roughness and surface oxidation. So here let's see the how the this ion irradiation works. So if you see a magnetic film is placed in the iron flux, like ion flux, so the here ions are used like argon plus, which don't react with the host material. Then the after irradiation of the fluence of the ions and with the certain energy, if you see the change in magnetic properties. These are the magnetic domain images. Before that it shows some magnetic nature, after that it changes its magnetic nature. What happens when you add this argon or the ions to the host material? If you see the ions, the interaction between here electron and host atoms, and of course the ion flow, there will be interaction among them. So if you see the ions and electrons collision, it's basically inelastic collision. Due to that, so it makes a dragging force. So in that way, so argon, that is incoming ion flux, that stops in between the material. So another interaction, which is the host ions, host material, and this argonal, that is elastic in nature. So that makes the displacement in the host atoms. So let's see an example, so which is happened. So here the main message is they are making the change, making the tuning of magnetic anisotropy by changing a crystal structure to the amorphous structure. You can see this is the like original material as grown sample after ion irradiation of different fluence values at a certain energy, they can tune the magnetic properties. And this is one example. Here you can change the fluence, and you can see the different types of magnetic domain, like a dense stripe domain to other kind of in-plane contrast by changing the fluence. And of course, when you apply the in-plane field, you can see the reversal of magnetic domain from nucleating and domain propagation. So if you see another one example, which is the rare earth and Thomson metal system, here the idea of tuning magnetic properties from the amorphous structure to make the crystallization behavior by changing the ion fluence, so uh, they can produce, or they can kind of create the in-plane magnetization in the system, or that's the magnetic softening, we can say. And this is published in last year, like from our group. And you can see the behavior of magnetic moment also, behavior of magnetic image. You can see the magnetic nature is softening after the irradiation. So basically you see the perpendicular at the unirradiated state, and while you irradiated, this goes on in plane contrast. And similar case, if you see a single layer, so this is again reported the last year, GTF and TBFE system. This is similar in a single layer 20 nanometer sample. This is irradiated with helium and neon ion irradiation. You see a compositional change after the irradiation. Along with that, this is the pristine state of the sample. When you irradiate it with the different fluence, you see the change in the magnetic hysteresis that says the magnetic anisotropy and other magnetic properties that changes. And here important thing is you can tune the compensation temperature if you change, or if you tune the here the ion irradiation, as well as if you change, if you can change. And here you can see the compensation temperature is tuned upon the ion irradiation of helium. This is one of the example I have shown here. Similarly, in Ne plus also it shows the similar nature. So here the idea is, in our case, if you see, we take a exchange coupled system where GTFE shows a soft magnetic nature, while TBFE shows a hard magnetic nature. We take a exchange coupled system. So when you take exchange coupled system, we have enough room to tune the magnetic properties depending upon your energy, incident energy and fluence. So in this case, we fix the fluence like 10 power 49 per centimeter. We change the incident energy of argon plus. What we observe from this is stopping range ion matter simulation. What we observe, the irradiation mostly happen in the top layer. And this is the Kerr magnetometry. You can see the pristine state where you change the as deposited state. Yes, we took the two samples, I mean two types of sample. One is we change the upper layer thickness just by to tune the magnetic anisotropy. You see the as deposited state, it shows the nice outer plane signal, or outer plane loops, where the in plane loops gets opens up when you irradiate with the different incoming energy. So then, yes, that was the magnetometry, MOOC magnetometry, to confirm with the volume measurement, which is the mostly VSM measurement we do. So there also similar observation we observe at the pristine state. We see the loop opening and loop get, I mean, slanted and closed. I say less coercive force when you increase the incident ion energy. And here we don't see, I mean, we are there in the intermediate state of ion fluence. There we didn't see any structural changes upon the ion radiation energy. And here another thing is we minimize the surface, as I mentioned in the motivation. So by the atomic force microscopy, we observe the surface roughness at the higher fluence, higher this is incident energy, we see less than 1 nanometer. And you can see the pristine state, we see the nice perpendicular magnetic domain. When you irradiate it with the higher kind of incident energy, you see the in-plane magnetic domain contrast, or the distorted magnetic domain. So then we'll go to the micromagnetic formalism to see the what exactly happening after the irradiation. As you see, the most of the kind of ion irradiated happens in the top layer. So we tune the top layer anisotropy. This is my top layer, middle layer, bottom layer. So it changed the magnetic anisotropy of the top layer to 0.2 to 0.5, this one. And what we observe when you change, and other magnetic moment keeping at constant, when you change the magnetic moment, you see the in-plane contrast appears here, and that also appears in the magnetic signal. You can see the cohesive field and the shape of the loop drastically changed, and that says if you see the change, if you change the top layer anisotropy, you see clearly demagnetization energy is increasing. That may be the reason here. So you see the cohesive force is much higher in case of higher value of anisotropy, while in the low case observed at the low value of anisotropy taken it. And you can see the squareness value also, it is higher in case of the higher value of top anisotropy, top layer anisotropy, while low observed in the low value of anisotropy. So that's come to my conclusion. If you see a tri-layer, it shows the intrinsic PMA nature, and yes, so we can tune the magnetic property without structural modification much of that. And this is, we have used the argon plus ions for different incident energies, and we see a spin reorientation from the out of plane to in plane, and where we measure different technique to validate this one. And then we have used also micromagnetic modeling to domain this model to understand this micromagnetic energy evolve here. So also this paper is now, I guess this is online. Yes, this is online published, and Abhishek Talpatra yesterday speaker, and me the co-contributor. I'm equal contributed here. So these are so coming to acknowledgement section. So I would like to acknowledge my guide from IIT Hyderabad, Dr. Jyotiranjan Mohanty, and our collaborator from DMRL Hyderabad, Dr. Arut Selvan, and all our lab members at IIT Hyderabad. And this work has been performed at a low ion energy beam line at IUAC, and for funding agencies are like ACRB board and Naval board. Thank you for your kind attention.
So hi Ajit.
Yeah.
So I have a question. So you have seen this shift in the compensation temperature. Right? So how much change actually you have observed?
Let me go to that slide. This is a paper published in 2021. So this is compensation temperature happens when you can, tune the this change. You can use this one and tune the ion fluence. Okay, so this will change the compensation temperature. And your question is how much is happening in my case, right?
Right.
So yeah, so for that I didn't observe for time being, so it's on the, plan. So for time being, but we expect compensation temperature will be around something little more than kind of room temperature, 300 or 300 to 350 Kelvin around, I guess, because this shows a tri-layer, and if you see a single layer, that's a different case. It's here, it's a tri-layer, so we expect little bit tuning from this case. And also we have seen in the other cases where they don't observe about this case ion irradiation, but by XMCD and all they observe similar range of values, compensation temperature, right?
Okay. My another question is, so you mentioned about this spin reorientation. So
Yeah.
basically this means by this irradiation, you are changing your, anisotropy from in plane to canted and then out of plane. So that's kind of systematic, change.
Yeah, as you mentioned, true, but there is a little change here. As you mentioned, my first thing is out of plane, then from out of plane to is coming in plane. You can see here, this is my out of plane signal. It shows clearly out of plane. One, when I irradiated with the different ion flux energy, you see the loop opening happening in the in plane. So basically, it happens from out of plane to in plane. That's mean of spin reorientation transition.
Sajid, you can ask.
Thank you.
Yeah.
Nice talk. So I have a question. When you irradiate your system, do you see some crystallization or not?
Not really. If I compare with XRD analysis, if you see here was like, you use little bit higher incident energy, 200 keV, where the fluence you can see 15 or 16 case, and you see from our first crystallization happen.
Then you
That
see a
that happens, but in my case, it's little different. We kept around 1014, which is intermediate, then you lower the energy. So we don't want to go for amorphous crystallization. So we want to be amorphous state, but we want to tune again the magnetic anisotropy. Okay, so we don't change. I mean, we were not aiming to change really crystallization in the sample or any formation of the crystallization in the sample. So we were aiming to be in the amorphous state as TA rather than transcendental shows amorphous nature.
Okay, thank you.
Yeah, welcome.
Okay,